So far, we've looked at different mole ratios, seeing how limiting and excess reactants can stack up to each other, and then comparing two different substances using their mole ratios. In the second section, we looked at some conversions. When you have the number of moles of one substance, you can find the number of moles of the second substance if you know the balanced chemical equation. And now in the third section, we will be adding grams to the mix in a way that we can actually measure things in a lab and transform that into the grams of a second substance. So let's dive into it. All right, so again, we're dealing with more stoichiometry, which is just the glorified, really difficult way of saying conversions, and using multiplication tables to go along with that. All right, so this is the problem that we saw in that last section, where we started with 6 moles of hydrogen, and using the balanced chemical equation, we were able to transfer that to the moles in oxygen that we needed for that, using this graphic right here, where we start with the moles of our first substance and set up a mole ratio to convert to the moles of the second substance. All right, so hopefully you've had some time to get acquainted with that, had some practice on it. So let's move on to the next type of conversion we can have, where it's actually gram to mole. And this graphic is actually very important. I want you to take note of that because it's actually a part of the overall map that we use. So if I can go ahead and take this away, you can see how there's still another part to this graphic where we can start, in this case with grams, we can follow a conversion to convert our first substance from grams into moles. And once we know the moles of that substance, we can continue to convert it to the moles of the second substance according to our chemical equation. So let's go. Before I get ahead of myself, let me go ahead and say that the conversion factor we're using for this will be the molar mass. And if you remember the molar mass from one of our past units, we get the molar mass from the periodic table. Every single element has a specific molar mass, which means that 1 mole weighs however much the periodic table tells us. And if we have a compound, if we have something that is a combination of 2 different elements, then we just add their different molar masses. Now, this problem is a little bit similar to the one we did before, but it's also a little bit different. Notice that on here, I'm starting with 6 grams of oxygen, and I'm asking how many moles of hydrogen will be used up in this reaction. But the process is still a lot of the same. It's just an extra step. It's a little bit longer of a problem. You might think of this as a combination calculation. All right, so let's go ahead and look at that. So let's see. We can start the problem in the same way. We just draw information from the problem, and in this case, we have 6.0 grams of oxygen to start our problem. From this, we set up our table, and we'll be setting up a conversion factor. If you look over to the graphic over here, remember that we're using the molar mass of this to convert from grams into moles. So now I need the molar mass of oxygen gas. So let's go ahead and look at that. Here's the title for oxygen as you would find it on the periodic tables. Now we have some information on here. Remember, the molar mass is this number that is set at the bottom. So 1 mole of oxygen has a molar mass of 15.999. We'll round that to 16.00. All right, and so this is the information that I'm using for setting the molar mass of my compound. Now, something to note here is that a single oxygen is worth 15.99, or as I said, 16. But notice that the chemical formula we have on here isn't just oxygen, it's O2, which means that we're accounting for 2 pieces of oxygen in this one. So instead of having our molar mass be 16, our molar mass will be 32.0 grams of O2. And this corresponds to 1 mole of oxygen, of O2. All right, so we can do this. See the units that we're using on here. Notice that here we have grams of O2 in the top left and grams of O2 in the bottom right. Because they're matching, but they're top to bottom, they will cancel out, and we're left with moles of O2 as our unit. So now remember that this table has the mathematical meaning. If we turn this into an expression, we get 6.0 times 1 divided by 32 is the calculation. So you can put this through the calculator, and the result they get is 0.19 moles of O2. So now we know how many moles of O2 we're using from the amount of grams that we started with. 6 grams of oxygen is the same as 0.19 moles of oxygen. Now we can take this amount of oxygen and relate it back to our chemical equation. We can move forward in our map here. Now, so we start with grams, we went through the conversion with a molar mass, and now we have the number of moles. Well, now we can go from this number of moles, use the mole ratio to get the amount of moles of our second substance. So in this case, we're trying to compare oxygen to hydrogen. So we'll pull that. We'll use this number, 0.19 moles of O2, as our next starting number. So here I'll copy it over, 0.19 moles of O2. From this point, I can set up a second table, and notice that in my map, I'm doing the conversion using the mole ratio, so I need a mole ratio on here from my balanced chemical equation. Remember, there's two ways to write this mole ratio. I can set 2 moles over H2 over 1 mole of O2, and 1 mole of O2 over 2 moles of H2. And the one that I need on this case is the one that will go to the bottom with mole of O2. So I'll be using this one on the left with 1 mole of O2 on the bottom and 2 moles of H2 on the top. So when I set it up this way, notice my units, mole of O2, I have both the top left and the bottom right, and they are the same units, so they will cancel with each other. So now I'm left with the moles of H2. If I simplify this into an expression and a calculation, I get that 0.19 multiplied by 2 moles of H2 divided by 1. If I go through and I put this into my calculator, I will get the result of 0.38 moles of H2. And so in these two steps, in these two calculations that we just did, we found the number of moles of hydrogen that will react with 6 grams of oxygen. And that's very useful because we just started with the unit of grams and ended with the unit of moles. So we've done a great big conversion in this step. For the last type of conversion that we can have, we're going starting from gram and ending at gram. So look how this works out. I have the graphic here again that we've just been using. We started with moles of one compound to the moles of the other one, and then we zoomed out a little bit to the left, saying that if we start with the number of grams, we can convert it to the number of moles by using the molar mass as a conversion factor. Well, we can also do that in the opposite direction, where we now have the moles of a second substance. We can take those number of moles and change into the number of grams of the other substance by using its molar mass. So now I have here the problem we were just working with before. We can just, we ended with moles of H2, so we can take it just that last step and to convert from our moles of H2 into the grams of H2. So let's go ahead and see that. It's the same process we already seen. It's just one more of these conversion tables. So we'll start with my information of 0.38 moles of H2, and I can set up a table around that, and I'll be using my molar mass of hydrogen. Again, this you get this from the periodic table. And on this one, hydrogen, my molar mass is 1.008. We'll round to just 1.00. And again, this is for a single hydrogen. Notice that in my problem and in my compound, I don't have single hydrogen, I have H2. So I'm counting for 2 pieces of hydrogen, which gives me the mass of 2 grams. 1 times 2 is 2 grams of hydrogen. And this corresponds to 1 mole of hydrogen. Notice that I set up the mole of hydrogen on the bottom so that I can cancel the moles of hydrogen on the top that I started with. All right, so if you do this, these units will cancel. My calculation in this case becomes 0.38 times 1.0. Just a second. All right, sorry for the typo. So my calculation now, when it's correct, it is 0.38 times 2.0 grams of H2 divided by 1. If you go through, you put this into the calculator, the final result you should get is 0.76 grams of H2. So now this problem, that's really all there is to it. These big problems that might seem really complicated, you're just doing 2 conversions at a time. So just in this problem and in every problem that you might see, we started with the grams of oxygen. In this case, we converted that into the moles of oxygen. Now, once we had the number of moles of oxygen, we can compare directly to hydrogen by using the mole ratio. So we convert from moles of oxygen into moles of hydrogen, and then once we have the moles of hydrogen, we can take that back to the grams of hydrogen. And the reason we do it this way is because we can't compare grams of different substances directly, because as you remember, every substance has a unique molar mass. It depends on what elements and what atoms it's made of. So, you can't compare 10 grams of oxygen to 10 grams of lead, because lead weighs a lot more. 10 grams of lead is actually a lot less moles than 10 grams of oxygen. All right, so that takes care of the math and the setup for these types of conversions. Once again, this is called stoichiometry, and it just means that we're dealing with either grams or moles in a balanced chemical equation, and we can exchange between the two as long as we have that balanced equation.